Quantum computing is useful today when it is connected to a disciplined engineering workflow. The question is not only whether a circuit can run. The question is whether a team can inspect the logic, measure the result, and decide what deserves the next unit of compute. The surrounding ecosystem positions quantum work as an engineering and orchestration problem. Code, execution, evidence, and operational control must work together. Before entering the product, the public documentation provides the technical context. In this lesson, we will verify each important claim through the authenticated interface instead of relying on marketing language alone. The platform also exposes a desktop entry point for teams that prefer a fuller development surface. Our demonstration, however, stays inside the browser so every interaction remains visible. Inside SynapseX, chat, work, code, and labs form different surfaces around the same working environment. Labs is the focus here because it keeps research workspaces, code, files, runs, and agent conversation together. The labs index shows persistent research workspaces. Each workspace is a place where a developer can preserve the context of an experiment rather than leaving the result inside a temporary conversation. We begin with a dedicated workspace named Quantum Experiment. This is the first practical control. The experiment has a named home for its code, messages, outputs, and future iterations. The authenticated workspace is now created. From here, the workflow is driven by a natural language request, but the result is expected to become a real artifact that the team can inspect. I ask the workspace to draw a Bell circuit and validate it in the free simulator. The request explicitly asks for the circuit code, execution trace, shots, measured outcomes, validation, and the developer inspection workflow. The workspace responds with a plan. It writes the Bell circuit, runs it on the free simulator with 1024 shots, performs a parameter sweep, and then explains how a hybrid developer should inspect the result. This is the classical control loop around the quantum experiment. The circuit becomes a real QASM file inside the workspace. That matters for developers. The experiment is not only a paragraph of explanation. It has a concrete circuit artifact that can be reviewed and carried forward. The verified run card reports backend sim, status succeeded, and the measured counts. This is a free simulator result, not a hardware claim, and the interface does not expose a paid price for this run. The acceptance criteria are visible. Only the expected outcomes, 0 forbidden outcomes, near balanced counts, convergence across shots, and an unbiased seed are shown in the result table. In this run, the observed split is 50.7% versus 49.3%, with the convergence indicator moving from 3.5 percentage points to 0.4. The educational value is the gate before hardware. The simulator checks whether the logic is correct. Real hardware would add effects such as gate errors, readout errors, relaxation and dephasing, and crosstalk. The interface explicitly says hardware should be considered only when the simulator cannot answer the question. Now we move to code. I ask for a developer-readable Bell circuit and an explanation of how a classical control loop can inspect simulated measurements before submitting any hardware job. This connects the quantum circuit to the software workflow around it. The code surface starts by inspecting the workspace and then prepares a clean demonstration of the classical control loop pattern. The key idea is repeatable iteration: generate, inspect, measure, and only then decide whether another backend is justified. The labs toolbar exposes the QCOS control. In this session, the visible control is QCOS off. That state is important evidence. We do not claim that a QCOS routed hardware execution occurred when the interface does not show one. Now we open Quantum QCOS. This panel exposes the governance controls around hybrid quantum workflows, the service state, endpoint, connection fields, provider settings, shot configuration, and hybrid simulation mode. We inspect the controls without changing or saving them. Next, open Compute Credits. This is the cost control surface. The account shows a 5,000 credit balance, while the product distinguishes free simulator work from metered compute. We inspect the balance and history, but we do not buy credits or change billing. After free validation, we open the comparison for an advanced classical simulator that emulates a quantum machine's noise profile. The visible proposal uses Qiskit Air with FakeLima v2, a calibrated noise model, and a local metered sandbox estimated at about 2 credits. This is a CPU-based emulation step, not physical quantum hardware. The run is still in progress, and the interface explicitly says that no physical QPU was dispatched. The expected noise comparison is visible, but there is no completed metered receipt or confirmed credit charge. We stop here, the user remains the approval authority, and the physical QPU path stays blocked. The Work Hub extends the platform beyond a single experiment. It provides access to scheduled tasks, skills, connectors, libraries, and instructions that can support the broader research and engineering process. Scheduled tasks is currently marked Preview. The page shows example workflows such as a daily stand-up summary and a weekly report, but it also states that automations are temporarily unavailable. No task is created, and no active automation is claimed. Connectors show how external context can be brought into an AI workflow. The live page lists GitHub, GitLab, LinkedIn, Google Drive, Gmail, Google Calendar, Google Cloud, Google Ads, and Linear, with a clear distinction between authorized providers and tools that are ready for AI use. We do not modify any connection. The Agent Store adds reusable specialists. The visible catalog includes data analyst, code review, security audit, and quantum advisor agents. Quantum Advisor is described as supporting quantum computing tasks, QCOS workflows, and circuit design guidance. We show the catalog without launching a paid agent run. Skills are reusable capabilities. The live page exposes web search, image generation, code execution, and document analysis, while showing that no personal skill has been created in this account. This is the layer teams can use to standardize repeatable research and development workflows. The settings inventory brings the operating model together: capabilities, quantum QCOS, compute credits, API keys, Git, SynapseX code, connectors, plugins, memory, models, and appearance. We inspect the available configuration without exposing credentials or changing account state. The complete path is now visible. A developer creates a workspace, writes a circuit through natural language, receives a real QASM artifact, runs a free simulation, inspects the trace and acceptance criteria, connects the result to classical code, and evaluates whether hardware is justified. For scientific teams and enterprises, this is the practical value of SynapseX Labs: make the experiment inspectable before it becomes expensive. Validate what can be validated classically, preserve the evidence, and keep the human in control of any paid quantum execution.